To get started, it looks like we have Josh Mode from Seahorse Geomatics, and the presentation is latest advancements in underwater inspections using echo sounders.
Thank you, everyone. I just want to begin by saying how excited I am to be at a conference again, to see everybody face to face and not have a Zoom meeting anymore. This is one of my first, conferences again since COVID. So, yes, my name is Josh Mode. I work on the hydrography side of things, so mapping underwater using sound. So I'm going to be talking today about a case study and kind of an overview from working with RDOT, working with Mike Hill and Kevin Weston in getting some equipment to them and showing you guys what that equipment can do. Briefly, I'm just going to talk at the beginning about, current detection methodology for scouring and, bridge inspection into the water. Talk about sonar. What is a multibeam? Just kind of start off with the basics so we're all on the same page. Go into the portability of the system and why I advocated for it for RDOT. Getting into what some of the data types that can be collected with this system, software that's being utilized. There's lots of different software packages out there. And then go into some of the products. What are we going to be able to see? What are we going to be able to do with some of that data? And then just talk really briefly on training. Back in September, kind of after RDOT got their equipment, and I thought that there might be an opportunity for me to come here. I tried to reach out to pretty much every DOT bridge inspection group within the United States to kind of get an idea of what other methodology is being used. I'm new to the bridge preservation, so this is my first time at this meeting and kind of talking about bridges. Most of my conferences and groups that I talk to are solely with underwater, so it's actually really exciting to be here and learn more about kind of this group and what you guys have been doing. But over that different calling of different groups, learned that divers are the main type of detection method, so putting people in the water, either hands-on or visual, depending on the water clarity, to see what's going on down there. And then, kind of before sonars, there was lead lining to create nautical charts. So still some groups are using lead lines, weighted lines, or pole in shallow water to get an idea of what's below the water line, what's going on down there. Side scan sonar is also being used. That's more of a visualization tool, kind of imagery. We'll talk a little bit about how side scan sonar differs from a single beam or multi-beam system. When I kind of started talking with Mike Hill and his group at RDOT, they were currently using a single beam system to look at, what is going on around bridge pilings and so forth. And what I'm going to be talking about today is the multi-beam system. Just so we're on the same page, sonar is short for sound navigation and ranging. So we're going to be sending out sound from a transducer. In this case, with a multi-beam system, it's going to be a little bit more complex than what you get at the Bass Pro Shop with more like a single beam system. So we have a transducer array and a receiver array that's going to be sending out sound. We've got an angle about how that sound's coming out of the transducer and a two-way travel time. So that's how we're going to be deriving these point clouds. Single beam system is going to be looking directly below the boat at nadir. You're only picking up 1 point per ping. Still pinging pretty quickly, maybe up to 50 times a second. With a multi-beam system, with the system that I'm going to be talking about today, we have 1,024 points that are going to be sending out and collecting data with each ping, again, pinging up to 50 times a second. So pretty dramatic difference there between the two. Multi-beam sonars, starting from some of the oldest to the left to the most new age that we have over here on the right, are kind of coming in this T configuration. Some of the older systems that you can see here, they're very large. They're separated, so they're not a coupled system. And then as we move to, kind of the one that has the old computer in front of it there, that's kind of was built in the 80s, 90s. That system there, it is in a T configuration. It's tightly coupled, but there's a lot of wires. And then you get, to a more new age system to that, which kind of branched off from that other company. But again, it's very big, it's very bulky. What you'll notice from those first three images to the one that you have on the right, which is a Norbit system, is there's a big dome on the front of it. It also, the receiver array is curved. Those are two key elements for why I recommended this system to RDOT for structure scanning, vertical structure scanning. That dome on the front is an IMU. So when you collect multi-beam data, unlike with single beam data, you have to know exactly what is the roll, pitch, yaw, and heave every time you ping. So you have to know where is the boat moving, so when it pings, you know exactly where those data points that came back from. If you're off by just a little bit, the data is not going to line up from line to line. So having this tightly coupled solution is really key in being able to set up very quickly. So the system that RDOT got was this system here. So this is the latest of the Norbit sonars. You'll notice compared to this first one here, there's no dome and the receive array is a little bit bigger. So that means the resolution of the data is going to be finer. You'll be able to see smaller objects, smaller holes, cavities, and so forth. You'll also notice there's no dome on the front. The IMU is now integrated within the transducer array. And that IMU is from a Planix, which in the marine community is a very well-known IMU system. So here we have a small system. I can easily pick this up with one hand. What we need for this is to be portable. It's great to have a system, but to be able to go to any vessel of opportunity is what I consider to be portability, not being able to pack it up into 5 different crates and ship it across for thousands of dollars across the U.S. So when I say portability, I mean being able to set up on this U.S. Navy boat in Hawaii. Now, other than this one, all of the other pictures I've taken. So meaning I've either flown out there with the equipment or they've already had the 2 Pelican cases there on site. So for example, this is one that we did a survey on in Pearl Harbor for the USS Arizona. This one is the Alabama DOT dive group. So this was one of the last actual demos I did before going out because of COVID. You know, everybody had to stay home. This was with a group that I've seen here, Collins Engineering. So this was in Jasper, Alabama, where they did a survey. And with this one here, I showed up with the equipment. And all they had were this boat. We grabbed a 2x4, put it on the side, got some clamps, some compression clamps, hooked this up, and we're out surveying within less than an hour. This is the U.S. Navy underwater construction team. Again, all they had was this vessel that they blew up in a 2x12. I came in with the equipment, and we did the survey that day. This shoebox of a boat is something that the Army Corps of Engineers wanted to try and put a sonar on. The way that they found the bottom before sonar, they hit it with the bottom of the boat. It's pretty cool watching this thing deploy, but it wasn't easy to set up on for the first time, but we were able to do it. This next one I like to show off just because, you know, it's a normal man's boat. You know, putting it up on a John boat, you know, this was the boat in Wyoming that they had access to. And so we're able to just go out there, utilize somebody else's boat, and do the survey in this pond that was on a farm. This is Wilmington District, so Army Corps of Engineers, which is usually I work with the Army Corps, USGS, US Navy, or contractors for them. So this was a fiberglass boat that we were able to set up, again, on that day. But most importantly, so being able to come out and set up on this boat. Now, I'm going to show some pictures later on in the presentation. But again, I came out here, I want to say it was 2019, and Kevin over there picked me up at the airport. So I flew in with these 2 cases. He picked me up. He took me out to the boat. All they had was a 2x12 across the front. I think that was the same 2x12 when we did the training that we used when I came down here for this demo. Collected the data that day. I processed it that night. I showed Mike and Kevin the data the next day and flew back home. So when I talk about portability, that's what I'm talking about, being able to set up on any boat of opportunity. To do that, we have to have, you know, everything compact. So again, you know, the idea of the Pelican case here, you know, everything's fitting into this. So we have the navigation antennas there. You've got, you know, navigation antennas here. Here's the sonar, a single cable coming from the sonar up to the topside unit. And in this case, they also have a laser scanner and a profiler. So here's our Norwegian model, Torben. He's product director. Just kind of give you an idea of how large is the sonar, right? It's you know, yay big, this long, not that large. But it doesn't matter how small the sonar is or how compact it is or well engineered, the pole that you're putting it on is what really makes this system portable. So we have a carbon fiber pole that's manufactured in the United States. So carbon fiber, it's very lightweight. It takes less than an hour to set this thing up. You can ask Kevin and Tori over there how long it takes them to set it up now. But minimal tools to set this up. You know, you actually don't have any tools on this. We can have wing nuts if necessary for short durations. But everything is dialed in. So being able to move the system from one boat to another, there are no new measurements that you have to take. All you have to do is set this up, and we've already pre-measured everything for you with this system. So, you know, being able to go out there, and in this example of kind of how lightweight this system is, so this is my colleague, Mike Munchler. So here we have, you know, the wing head sonar over there on the right, everything, cables all hooked up, and he moved everything from this boat over here and then redeployed it on this boat over here on the left. When I showed up here for the first kind of RDOT demo, this was me coming out of the airport. This wasn't me precisely, but the idea of having 2 Pelican cases coming off of a plane. So when I talk about portability, this is what, you know, I'm really talking about. So now we have the ability, you know, to set up on any vessel of opportunity, whether it's, you know, more of a larger survey vessel, an ocean going, you know, a John boat, USGS, U.S. Navy down here in the middle. My favorite is the USGS Missouri, where they decided, well, we want to set it up on a canoe. It's like, okay, well, we've never done that before, but hey, now we know that it's possible, right, for those hard-to-reach places. This is one that I recently got from the U.S. Navy. I can't say where it's at, but their boat broke, and so they went to a hardware store, bought what looks like a 4x6 piece of wood to put it on the back of this boat, and you can see they just have a whole bunch of compression clamps over there on the left holding everything together. So lightweight, truly portable. One of my favorite pictures, though, now is this one that Kevin was able to send me. So, you know, setting it up on any boat of opportunity and going out and collecting data wherever needed, whenever the opportunity really arises. So what are we getting from this? You know, I've talked about a sonar, multi-beam system, it's portable. You're going to be able to get something called bathymetry and imagery. So bathymetry is going to be your point cloud. It's going to show what does it look like under the water. The imagery is going to tell you what is the material type, right? So we're going to be sending out sound for bathymetry. We've got a 2-way travel time at an angle. For looking at the imagery, we're sending out 100% signal, sound, energy from the sonar. And then based on, you know, the water column, there's going to be some sound attenuation. It's going to dissipate. But depending on what type of material you hit, it's going to be very reflective, or it's going to absorb some of that sound. So now we can tell, hey, we can see different types of material on the bottom. We can see concrete versus rock versus sand versus mud versus different types of, you know, mud in the area. So you can start not just seeing what's down there, but start being able to quantify potentially what is down there. So with this system in particular, we have 2 types of imagery that we can collect. I just use different color palettes for the 2. They can be in both, you know, copper or grayscale, so don't think about that as the difference. But one is snippets collected with the multi-beam, or true side scan, where we actually turn half of the receiver array into one receiver, the other half into another receiver to collect actually true side scans. So with this multi-beam system, you're collecting bathymetry, water column data as well, which I'm not really showcasing here, and side scan and backscatter. This is another thing that I wanted to show off from the Alabama DOT survey. That was in Jasper, Alabama. It's really hard to see here. You can't, oh, maybe you can see up there. We're in 176 feet of water. And you'll notice here in the top, up here you'll see all these little dots. Well, down here it's much easier to see what we're looking at. This is a forest where the water is a man-made lake. It was flooded very quickly, and here you can see the entire forest underwater. In the side scan, you can see a couple of the dots up there, but looking in the bathymetry, this is what it looks like. So here we can actually see, you know, underwater and tell what's going on down there. So I mentioned a couple of times about the curved array. Well, with all those flat array systems, you're really only, your maximum swath, you know, where are those 1,024 beams, are going to be pointed straight down, right? Maximum maybe 180 degrees, theoretically. You're really going to get to 175. With the curved array system, our maximum swath is 210 degrees. Now, most people aren't going to survey at 210 degrees. In this example, they were. So this is a lock and dam behind Heathrow in London. And so here they just want to do one pass to see what's in there, exploratory, right? What most people are going to be using that is, instead of having a large swath, is to be able to point your swath to port or starboard without mechanically moving your sonar. So on the fly, to be able to say, I want to see what's over there up that embankment. I want to see this vertical structure. Or now I just want to point straight down without, again, moving your sonar, because when you move your sonar, your points of reference change, and then you have to stop the boat. You have to do all new measurements, and that's a big headache. So here, we're able to see from the water surface all the way down. And because of that laser scanner that I was talking about that RDOT also got, now you're able to get images that look like this. So we're able to see the topography and meld that with the bathymetry underneath it. So to make this work and line up perfectly, you have to have really good software, right? Two of the software packages that I talked about with RDOT was something that Norbit makes, a data collection tool, very simple to set up project, and the other one was a QPS suite. In here, within the United States, QPS is a name brand. Another one is HiPAC. So if you guys have heard of HiPAC before, QPS and HiPAC are very similar in what they do. So the data collection tool, it's something that comes with the Norbit sonar. To give an idea of what you're doing, you just turn it on. You don't set up a project, and this is what you would see. You've got a boat seeing where you are. You're able to see the data that's being collected by the sonar. It's not super real time. It's about a 5-second delay, but you're able to see where you are, what the data looks like, and the boat driver can start going back, and mowing the lawn, painting underwater so you can collect all your data. So this is an easy setup, but it doesn't collect the laser scanner data. If you want a more robust setup, you have to go ahead and set up your project. There's a little bit more setup in that case. But here, again, you're able to set up everything so you can visualize where's the boat, what's underneath it. Here we're able to see, a point cloud data. Here you can see the pilings, all the way up to the surface. You can see that as well up here. And then we've got a model displaying that as well. And down here we'll be able to see overlap when you have multiple lines. So different types of software packages depending on what you want to see at one time, how much does it take to set up. With DCT, there's no setup. With this one, you have to, again, set up a project, set up geodesy, and so forth to make sure everything overlaps. So once you collect the data, how do you process it, right? What do you need to do to get to that final pretty point cloud that I showed you? So in this case, they are recommended Chimera, another QPS software to bring the data in. So here are a bunch of lines. We've got 4 bridges. 2 at the top, 2 at the bottom. Going in, we can view the data in a point cloud and a slice editor. So here we need to start going through the data to clean out erroneous soundings so our final point cloud, make sure it lines up, which here you can see we've got good alignment between all of the different lines. So down here, multiple colors here reference a specific line that was collected. You can see our lines over there on the left and the colors next to them. So here we're just looking at the river bottom. Now I've got a new slice up here at the top. I keep on pointing. Let me use my pointer right here. Up here, we've got another slice, and here we can see, the bridge pilings, right? You can see underwater. You can see those vertical structures, and we can start to see, hey, there's something around these structures over here. What could that be? So we have a couple other tools. So this is just a slice editor, but we can come in and look at everything in a 3D view. So now this is looking down at the 3D point cloud. We can see that we've got, some trees that are around this area. Here is our structure. We also have a cable, going through here, but we can start to distinguish all of these different features, get measurements, or quantify. Kevin went out, Tori went out, collected this. Year 1, come back a couple of years, what does it look like? Has there been any erosion, aggregation, and so forth? And as well, going down and looking at the laser scanner data as well. So here, the bridge is rotated, so I'm looking under it, looking up. So I can see my 2 bridge pilings here and looking under the structure to make sure everything's correlating together. To process some of the imagery data, we're also using a QPS suite called FMGT. So this is where it's going to go through, allow you to do statistical analysis, and start to build that mosaic. Again, the mosaic being what is the material that you're looking down at the bottom. Then kind of getting into the product visualization of everything, of being able to see all this data. Again, this is that same snippet, that area, those 2 bridges in the upper left, where we can again see, hey, there's some trees in this area over here. Something's going on. Something's, around this feature, and there again are those cables. So I want to showcase that demo that I was talking about when I came in here and, got picked up at the airport, 2 Pelican cases. Came out to, this was in Little Rock, went up to that same boat that you guys saw a second ago, and we went out to investigate what's around this little circle here, this red circle, there's nothing there. Well, actually there is, but at the time something had hit that structure that was, protecting the bridge piling. I think there was maybe a flood event a couple of weeks or a month beforehand. And so what you see in this yellow square down here is what we're looking at over here on the right. So here is looking at the model. Again, you can see the sand ripples. Looks like there's some rock being exposed over here. And you can see at this part here, something is smashed in to this structure, and now we have some of the rock is spilling out of it. So again, coming out here, showing them, hey, this is what it looks like. The one right below it, you can see everything's correct with that one, right? We can see that, hey, there's no issue with that structure. So being able to go out and say, hey, this is what it looks like before you put divers in the water. So I'm not advocating, of course, that you don't use any of the other, diver detection or lead line or side scan or not. But before you put somebody in the water, this can allow you to investigate that no matter what the water quality is and so forth. Here's a couple of other pictures. This was taken in Portland, Oregon. So this is looking, down on top of an I-5 bridge. So this is the model that's being created from the point cloud, and this is the actual point cloud itself. So again, being able to go out, look at the data, and collect measurements. Got a couple other pretty pictures here because everybody likes to look at pretty pictures. This is one from Europe. So this is in, I want to say this is in Hungary. And here, this is a bridge that was destroyed during World War II. Nobody knew that it was still down there. And so when they went out and surveyed, they were able to see, this old wreckage directly below their new bridge. And able to make decisions based on that. This last one is, again, that same data set we were looking at from RDOT. So again, now we're looking at everything put together, point cloud, bathymetry, or topography and bathymetry here. Clearly you can see different trees. There's some structures that are up here in the water, potentially causing some scour around that. And whatever this pipe here is, I don't know if that's supposed to be curved, but it can see clearly that it's moved maybe away from where it's supposed to be, and you can see there's a tree caught in it as there. But again, being able to go out and see these visualizations so you can make quantified decisions based on this, not based off of just, a diver going in the water and saying, this is what they say, but being able to see it, for yourself. And then being able to do repeat surveys to go out there and collect it again. So I'm going to end just on training because, again, Seahorse Geomatics, we don't do any of the services. That's other contractors out here. That's what they do. So, again, what I'm doing here is saying, hey, this is technology. Based on what you guys need, here's the different packages that I think might work, and then come out in there and do the training. So I just wanted to mention training because, we do usually provide training depending on point of sale at that time. But in 2022, we're going to be doing a lot more trainings open to anybody that wants to do one. So we're going to be holding an open training on the West Coast in Portland, probably in April, and another one at the Army Corps New York district, their facility, probably around July, August, as of right now. So any of you that might be interested in not just wanting to do this yourselves, but wanting to be able to have the knowledge so you can get your contractors to say, this is what I want you to do. Or as a contractor, be able to say, hey, this is properly what I can do in this situation if you're wanting to get in this type of hydrographic survey. Thank you so much for your time. Are there any questions?
This is real interesting. Thanks so much, Josh, for being here. Do you have to do some sort of ground setup for this in terms of, so you have the reference for your survey? What does that entail?
Yeah, that's a great question. So for the survey, we recommend setting up a real-time correction service. So that can either be through using a service like Ntrip, using a local core station to figuring out, getting centimeter level accuracy. So that's, something I failed to mention in this presentation, but I was thinking about at the last moment is how accurate are these point clouds? So when you're going out there with using like an RTK through either a base station that you've set up, that's broadcasting to a radio to the topside unit of the Norbit system, you're looking at about 2 centimeter accuracy, vertical or horizontal, about 3 to 4 centimeter accuracy in the vertical. So yeah, definitely setting up that RTK beforehand I mean, you could use, just satellite-based, but that's going to be about a meter accuracy, so definitely want to be more than that. All right, thank you guys again.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.